Okay, so here we go on to chapter 9, which is the second of the two chapters. Chapter 8, chapter 9 combined will be one exam for this class. And it's a topic near and dear to my heart, and that is differential equations. So a lot of people wonder, what exactly is a differential equation? Your friends ask you, what's a differential equation? Well, here's kind of how I see it, and I'll give you a very important, in my mind, an important differential equation. So differential equations. And so here's one of my favorites. And this is d squared u dy squared equals 1 over mu times dp dx. Okay. And in this case, u equals velocity and p equals pressure. So what does this mean? Oh, and then mu, I should mention, is a constant. In this case, it's a constant that stands for velocity, or viscosity. Like honey and water have very different viscosities. So what does this say? It says that the second derivative of velocity, u is velocity, the second derivative of velocity is somehow related to the first derivative of the pressure. But in this case, it's the second derivative of velocity with respect to y. So if I had, let's say, the walls of a pipe here that looked like this, and this is a pipe, and then I said that there's some big pressure here and there's some smaller pressure here, so that means that in this direction there is some dp dx. As I move in the x direction, the pressure changes. Well, the velocity changes with respect to y. And if I were to sketch this out, what does it look like? The water in the pipe would flow with what turns out to be a parabolic velocity profile. Now, you guys may have touched on this in your physics class, but it's just one of the many, many cases where differential equations govern something that happens in the real world. It's not as easy as if this then this. It's usually a relationship between derivatives, a relationship between rates of change. So I'm going to give you an example of a really basic differential equation, and that would be, let me do this in black here. So kind of what does a differential equation mean in a more more abstract but more familiar. So if I just draw the xy plane here, and I could write some, this is a different problem too. These are different. If I wrote some problem that said y prime, I'll write it this way: dy dx equals x times y. Okay, so what does this mean? It means the slope of this function at any given place is the product of the x-coordinate and the y-coordinate. All right, well, let's think about what that means. So in orange here, well, here it's 0. X times y is 0. Well, in fact, anywhere along the x-axis, x times y is 0. So all I'm drawing here are just kind of tangent lines that indicate the slope. So all along here, anywhere y is 0, the slope will be 0. So the orange is always just going to be the slope. And so anywhere along the y-axis down here, the slope is going to be 0. And so as I go this way, as x and y get big, the product of x and y is really big. So this kind of goes like this. And as x gets slower, it becomes more like that. Likewise, as y gets slower, the product of x and y gets lower. And then they kind of gradually get bigger as we go this way. So we have this kind of strange, field, and this is called a slope field of things like this. So these are all the potential slopes. Now down here y is negative, so it's going to stay negative like this, and then down here it's very negative because x is a big positive, y is a big negative, and it kind of goes like this. So another way to think about this is if you were as the direction that some water is flowing, or the current in an ocean. Let's see, and over here, how's it going to look? It's going to be negative this way too, so the slope is going down. Here it's very negative, and then it's not quite as negative as we go this way. And we go like this. And then here it's going to be positive because both x and y are both negative, so that goes like that. And then it's very positive down here and less positive as we approach this axis. And same deal kind of happens here, and then in here we've got a bunch of various slopes. And it'll look something like this. Very crude, obviously. Okay, so I kind of think of this as the current, or the direction, the slope. But depending on where I'm dropped off, so there's a lot of options here. If I get dropped off, let's do this in dark red. So drop off, say a rubber duck. If I drop the rubber duck off right here, it's going to kind of follow along in the direction here, and then it kind of goes like this. So, and if I say dropped off in a different color, drop off a beach ball, so I could drop that off over here, and it kind of does something like, this. Or I could do, a bunch of other colors, depending on, I should do this one in green, depending on where I drop this thing off. Likewise, I could do it in purple over here. If I dropped it off here, well, I can kind of, knowing what happens back here, I could backtrace it to where it must have come from. Okay, so what does this mean? It means that for any given a differential equation, has many solutions. So I don't just get one unique f of x here. I don't get one unique function. There's a whole family of functions that could fit the kind of slopes that I sketched in here. So that's really, one of the important topics of 9.1. There's really not a lot of stuff to do in 9.1, but it's more of a conceptually hard to think about. All right, so what if I have an easier differential equation? Okay, and the diff-EQ, you often hear people talk about diff-EQ as differential equation. And so a really common one is dp dt equals k times p itself. And this is where p is population, and t is time, and k is some constant again. These diff-EQs always have some sort of constant in them. Almost always. All right. So what does this mean? The change in population with time is the product of some constant times the population itself. Say if there's only 2,000 cavemen living in the world, well, a realistic population rate might be it only gained by, 20 people a year, 30 people a year, something like that. 30 babies born out of 2,000 cavemen, right? There's not going to be a lot of babies born. But when there's 7 billion people on the planet, 7 billion as there is right now, there's going to be millions of people born every year, right? So it makes sense that the change in population is related to the size of the population itself. Okay, but what if I want to know what is the population, right? I want a nice clean function. So what I can do here is I want to get all the p's on one side, the p's and the dp's. So I'm going to try to isolate some variables. So I want to get the p's over here, I'm going to get everything else over there. So I'm going to say that 1 over p times dp, so I divided by p, equals k times dt. Now this is starting to look interesting. What could I do here? I could integrate. And then I'm going to be well on my way to having some function. So I can integrate these two sides here. And what does that give me? Well, that gives me the natural log of p equals kt. Now, you might think I've got to add a c to one of these sides, right? So I'm just going to add it to this side. Well, don't I have to add a c to this side? Well, not ever. I'm just going to take my c and throw it over here. Okay. So we can shuffle this around, and we said I could rewrite this as p, rewrite it in exponential form. P equals, well, that's the natural log of the base here is e, and this is the exponent, so e to the kt. But we also, there's a c here, so it's also e to the c. All right, well, e to the c, that's just some number, right? So that's just times, e to the c is a constant, just like c is a constant. So I'm going to say that, let's take this up here. So let's say e to the c equals some other constant. And I'm going to say that equals the initial population. Okay, so I could rewrite this whole thing as the population at any given time equals some initial population times e to the kt. All right, now you guys have seen this before. You've seen this in college algebra or your pre-calculus class or whatever, where the population is the initial population times e to some growth constant, right? So k is the growth constant. So really pretty simply, by integrating this thing, we were able to discover we were going to go from a differential equation that just says that the growth rate is related to the population itself to an actual function, an explicit function for the population based on the initial population and the growth constant. Okay, but again, we need to know an initial population because that initial population really is kind of like our initial point that we drew in this other slope field here. We got to have somewhere to start to figure out where we're going. All right, so that's one of the most basic differential equations, and I think that a lot of the homework relates back to those. And one cool thing about differential equations, check, we said that population equals some initial population times e to the kt, right? Well, we started with population, the dp dt equals some constant times the population. So what we do is we take our population function from here and we stick it into there and see if it works out the same. So let's try that. So dp dt is really d dt of p0 e to the kt, right? Well, what does that equal? Equals, well, we can pull the p0 out of there, times dt of e to the kt equals, well, this is just p0 times, let's see, k, right? The derivative of the k comes down here, times e to the kt, right? Well, we've got a p0 on both sides, so we get out the all-powerful red pen of cancellation there. That's nice. And go back here, we can say that ddt, or d, what is this thing here? This is actually p. This is p. So we can say that dp dt equals k times this, but oh, look, this is p as well. That's p, so k times p, right? So starting with our original differential equation, substituting in our function, and blah, 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 it better work out that we get our original differential equation back. Okay, that's got to work like that every time. I just realized I'm not in full screen here. All right, so that's that. Let's do an example of this population. Let's talk about rabbits. you know, that book of Mice and Men. So this is the Of Mice and Men example. So let's say we're starting with 10 rabbits. And we're going to say that dp dt equals 0.1 p. So what does this mean? The change, and let's call it, I don't know, t is in weeks. I mean, I don't know anything about rabbits, so maybe this is true, maybe not. I read the book a long time ago. So t is in weeks. dp dt equals 0.1 p. So that means the change in population of the rabbits per week is 10% of the population itself. All right, so let's say let's make a table here, t in weeks, and then say pt, and so that's the population at this given time. And then so we'll say this is dp dt. Okay. So we start at t equals 0, we start with 10 rabbits, and then that means we're going to increase by 10%, which means that actually that'll be 1. Right? So we're going to gain 1 rabbit. So that means at week 1, we're going to have 11 rabbits, which means our dp dt is going to be 10% of that, 1/10 of that, so it's 1.1. So at this point, we're going to have, you know, we've gained 1.1 rabbits. Whatever, I mean, 1.1 rabbits doesn't make sense. A fetal, in utero rabbit. And then, so now we've got 12.1 rabbits. Well, our dp/dt is going to be 0.1, 10% of the population, so there's 1.21 rabbits. All right, so then week 3 comes along, and we add this 1.21 to here, so we get 13.31, and then 10% of that is how much the population is going to grow this week, is 1.331. You can see how this just keeps going. 4 weeks go by, and then this, let's see, 13.3 and 14.641. Okay, and then, you know, this is just going to go on and on and on and on, all right? And what this is called, now, this is not exact, right? Because I skipped a week, and I'm skipping weeks. Remember from compound interest problems that if I did it per day, right, and I adjusted this per day, it would be different. If I did it per hour, it'd be different. If I did it per minute, like for bacteria, you wait a week, you're really missing a lot of growth in bacteria. So this is a really simple numerical approach to solving Diffie-Q's called Euler's method. All right, and so that gives us a kind of a you know, an approximation for what really happens. Because if I were to look a little more closely here, and we did this, the formula that this would yield. So Euler's method come back, yields a formula like P equals the initial population plus 1 plus the growth rate raised, you know, to the t exponent, right? This is our compound interest formula. But in reality, P equals P0 times E to the KT. So this is analogous to compound interest. And this is like continuous interest. In the real world, most processes happen continuously, right? Everything's always changing. Unavoidable, man. Everything's always changing. So last thing we're going to look at, the last little, really rough introduction to a topic is called integral equations. All right, so what does an integral equation look like? Looks something like this: y equals 2 minus the integral from 0 to x. Okay, so we've got a variable up in there, and then we're going to say like 1 plus some function y. I'm just going to say y of t. I'll explain that a little bit more later. Sine of t dt. Okay. All right, well, what's going to happen when we integrate this thing? This is all in terms of t, but then we're going to stick, it's a definite integral, we're going to stick an x in there. And then we're basically going to replace our t's, this function which is in t now, like the dependent variable is t, we're going to wind up with a different function, the antiderivative of this, in x. All right? But oftentimes we want to convert these integral equations, which are really hard to work with. Inequations are hard to work with. All right, so instead we're going to say, take the derivative of both sides. All right, so when we do that, the derivative of y, well, that's what we're after, dy dx, equals the derivative of 2, well, that's nice, that goes away, minus the derivative of this whole thing, 0 to x, 1 plus y of t, sine of t dt. It's like, holy cow. This is going to be a seriously hassle of an integral, except that, according to the fundamental theorem of calculus, fundamental, and I think this is section 5.4 in your book, the fundamental theorem of calculus, right? We know that dx of the integral from 0 to x of y of t dt really just equals, well, the derivative of the antiderivative equals really just y of x. So we can just basically swap our y's for our x's and say that, so dy dx from down here, yep, that doesn't work, dy dx equals, well, the derivative of 2 went away, so it just becomes that 2 shouldn't be there. I got another mistake. Oh no, here we go. It's 1 plus y of x sine of x. And that should be negative, right? Because it was negative down here. So we then converted this integral equation, which they show up in the real world, the scientific world, once in a while as well. But that integral equation turns into a differential equation by taking the derivative of both sides. So I think that's all I've got for differential equations, kind of a numerical approximation of differential equations, and converting an integral equation to a differential equation. It's hopefully not too bad for you guys. Take a crack at it, and we'll talk about it more in class tomorrow.